Hello everyone. Today we're going to do a hover vehicle. Basically, I'm thinking of designing a hover bike. This was one of the senior design projects that I proposed for my undergrad, but I guess we settled on designing a ice chest, a motorized ice chest, and we presented that. But yeah, I wanted to do this since those days, and then I've said, why the hell not? And these two images over here, I sourced it from Google, and they're right here. This is the image, and this is the image, and the other one is right below that. So yeah, these are labeled for reuse. Whoever owns it, but I'm just reusing over here. So basically, we're gonna start off with a untitled document that's clearly empty, and here we go. First off, I have a process in mind. So the design process for me, this is clearly unique to me, of a hover vehicle. So first of all, I want to know how I'm going to, there's a lot of thinking going on around here. I'm going to think out loud. So first of all, I'm going to think how do we power the vehicle? That's the first issue. Second issue is what's the minimum and maximum payload? For me, the first thing is like the minimum and maximum payload, but then again, it's like a snake eating its own tail. Because if you really look at it, how you power the vehicle depends on like the current given standard. If you use like diesel and all those unsustainable fuels, I'm not going to do that. So that means I have to go with something electrical or nuclear, and I don't think nuclear is an option because because of the given risk. So at the current state of time, at least in 2020. The other is the design specification. So I think this will be impacted a lot by the first and the second. And one more other thing, the cost. So these are the four questions that are actually bugging me at this moment. So based on this, I'm going to design the vehicle. So let's do literature review. So the first question is, when we're doing this, the first question is going to be, how do we power the vehicle? For me, the obvious answer would be there's only two options. One is steam powered, and I know you're gonna like be like, what are you talking about? The other one is electric power. Now what we're going to do is this is heading 1. Heading 1, right? So I'm gonna make this heading 2, and much more easy for me to, if you really look at it, it's easy for me to navigate over there. This one is going to be heading 3. It's going to be heading 3. So it makes it easier for me to, these are only the 4 parameters. I know there are more, but then I want to streamline the process. Yeah, I don't want to do that. Yeah, so that's just for that. So yeah, this is the how do you power this vehicle, right? So the first question is going to be steam power. For that, you need to know how much energy you're going to apply. Then again, it brings us up to speed on the first question. What's the minimum and the maximum payload? Wait, this. Let's go. The minimum and maximum payload of any vehicle is dependent on its use case. So let's say if you want to use the vehicle to transport humans, wish to use the vehicle to transport humans, the primary objective of this phase of the design process is to create a minimum so since so basically what I'm trying to say over here is, so you want to either figure out if you're going to use this for distributing load, or is it for distributing humans from point A to point B. And I'm thinking about using it as a vehicle for, helping humans travel from point A to point B. So the first design concept is going to be, what do I need to do so that I can answer all the questions. And the thing about engineering is you don't want to go in this wide spectrum. You're working within these limits. And for me, it's always going minimum and maximum. What are my limits, right? So here's this engineering principle of design between minimum and maximum. I think it's worded differently, I think. Yeah, so just if you don't know, if you're getting into it, I was taking a class, and so to the whole principle of design is a very interesting thing. And this is one book that I would think, if you are into mechanical engineering, any design process, Shigley's design. This is a book, okay? This is a book that you need to, actually. This is a book that makes you want to cry a lot, but then again, it's one of those things. So what I'm going to do right now is focus on the design process itself. I don't think the internet is helping me a lot over here. So let me talk a little bit about, let me write up a little bit on this. Okay, the design process needs to, and so I'm just thinking out loud here, okay, until that thing loads up or my internet comes back. The design process needs to answer a few fundamental questions that need to, I think it would be easy if, yep. So I'm gonna do that. I'm gonna do that. And I'm gonna design process of a hover vehicle. That's good. The design that need to be answered for the design meters, I don't know. The design parameters. Meters are crucial to create this pinch concept that is feasible within the tools provided to the designer. So the thing about it is, I am not actually going to make this, because to make a hoverboard you need like a bunch of engineers. You need to have, this is a vehicle, and you need to have all those important documents, like yeah, this is the book I'm talking about. This book is your friend, okay? And it's going to always help you out, regardless. And this dude has uploaded the, don't download it, get it off the proper channels. So yeah, so we've got that. Now what I'm looking for is design thinking. So I'm gonna explain to you how I've been design thinking. So yeah, there's these, okay, Stanford D school design thinking process. This is a very good thing. So okay, so first thing is empathize, define, ideate, prototype, and test. So I'm emphasizing I need to do all of this. So I'm skipping up this, but defining and all of that, I'm straight jumping into ideate, prototype, and test, because these two areas right now currently I don't need it. But then if you're trying to do a business, or if you're trying to market it and do all of that, these two processes are like really important. So I'm basically doing this. So the ideate process, okay? So there's the prototype and test. That comes in if you have some money, or if you have something to do. Actually, all of this comes in if you have money, but then I'm trying to focus on the ideate. You share ideas, you there's like bunch of things that you need to do here. But if you want to learn more, just go to the school, Stanford EDU, and you get the idea over there. So so based on this, what's the minimum and maximum payload? So my brain, so what you need is so if I want to, the payload for me is humans, right? So I want to know what's the average weight and maximum average weight of minimum average weight and maximum average weight of humans. So that is the average weight range of different countries. So weight range humans countries. So body weight. So the thing about it is they have given a lot of by region. Yeah, this will be easy. Oh yeah, I forgot. I need to have references. I need to do that. Boom. So I need to have references, right? And then I need to do this. Boom. So where's number 12? Now you know. Don't quote Wikipedia, quote the sources of Wikipedia. The weight of nations and estimated of biomass. Son of a beautiful mother. Boom. Biomass. What's the name of the lady? Just say Sarah Catherine Walpole. Oh, sorry for the other authors. Yeah. That's it. And then what I'm gonna do is copy paste so that y'all can do whatever you want to do. Okay. So what I'm going to do is I think I'm gonna create a table. Oh yeah, I don't think I need to do a table, but I might need to just okay. So what I'm gonna do right now is I'm gonna snip this. There's this neat tool where see, neat tool. So I don't need to go around, create a table, and do all of that fancy stuff when I've got this awesome thing of neat table. So average body mass of humans in different continents. Oh, that's this funny. So all countries have a BMI distribution of Japan. Japan is the lowest, and then turns out USA is the highest. So if I take these two, I think I'm in a good position. I don't know. Everybody in different continents, and as I was saying, format text. If you don't know how to do this, just that's how I quote my research, okay? And you remove formatting right there. Boom. Goes back to wherever it was. If it's not clear, so now what I've done is, so based on this, based on the above table, we have the average the highest body average body mass of North America at 80.7 kilograms, and the lowest at, so if you really look at it, if I could go with 58.8 and 74.6, but then I want to go with the lowest and the highest being 80.7, the lowest being 57.7 kilogram, with a factor of safety of 3. We should reach at a higher payload than we have estimated above. So here's the thing. So what's a factor of safety? That's your question right now, right? Factor of safety. better yet, just go in Google Scholar and then explain to you what factor of safety is. Factor of safety engineering. Okay. This would be actually useful for our. So yeah, basically what you're trying to do is you're trying to balance the hazard with the controls, and I'm shooting off with a hip here. So you have your hazard on this side, hazard side, and you have the control side. So what you're saying is right here, my minimum weight that I'm saying it, like the minimum weight that it has to do like a payload, so that it's 57.7 kg and 80.7. Why I'm putting, like, let's say you could think like, okay, I want to go to the maximum, I only want to have a maximum load. That's for passengers. But if you have a minimum load, what it's going to do is, let's say a hovercraft is a vehicle that's going to power down. Yeah, I need to explain to you what a hovercraft is, right? Yeah, I should have started with that, but then again, hover vehicle is something that, well, I'm just assuming that you guys know what a hover vehicle is. That will not require friction from the, it won't require friction from the ground or earth to propel itself for motion. I don't know. I just came up with this. I don't know if you need to quote someone or do some research. I don't know. It does fundamentally hover vehicle should not be in contact with any surface and should at least let's say 1 feet up and should be in air at all times of operation. So yeah, so basically that. And yeah, so they call this a hover vehicle. I don't know That is true. You know, our drone is a hover vehicle. It's a funny thing. We're gonna get into that for electric power. Where's a good one? That's a yeah. NASA has a good one. Don't worry, I'm gonna give them the credit. Concept of a hover vehicle from NASA. Let's go to here. I know it's not a hover vehicle, but you know. For me, it's a hover vehicle. Yeah. Yup. Vehicle. I don't think it's a hover vehicle to begin with. It's like a lunar vehicle, I guess. But then it's gonna fly. It's gonna hover. So yeah, you could literally go click here and then use that. Oh yeah. So they're given the design specifications here. Maximum takeoff load. See? They've already given there. Oh yeah, I forgot to put this there. Trust me, I was so how do you power the vehicle? So I did not forget. The thrust and everything that goes into that part, okay? So how you're going to, you know, power up the whole process of, you know, making it into a vehicle that actually travels everywhere else. So you have this. So we're talking about factor of safety earlier. Let's go back to factor of safety. I'm so spread out, guys. So we have factor of safety. So basically the factor of safety thing about it is you have to do literature review every freaking time. I know formula for factor of safety, but because I have to give credit and I can't just pull it out of my ass. Go for textbooks, don't go for yeah, I'm just gonna use theirs. Fair enough, right? Safety and health principles and definitions. Guidance book. Trust me, if people are doing it something like in a different method, I want to know. Teach me how to do it right, okay? Just don't let me go like all goo goo and gaga or like my own method. Sometimes I like. If you go the other route when you're doing the literature review, trust me, it's gonna take way more time to do this. You have to go to a professor and say, this is the research that I'm using, and these are So why I'm using a factor of safety? Why am I use a factor of safety of 3? That's a question, right? No, I'm gonna pull the particular reason why we use a factor of safety of 3 is because we want the payload. So my assumption is, okay, this is purely an assumption, and this is a device that I'm designing. I'm currently in the we want the payload to have a safety net higher than 100%, right? So what you're doing is, let's say you want you have a payload of what you have a payload of let's say 100 kgs, and then you're trying to go on a different like tangent or somewhere else where the gravity is about the gravity has changed for some reason, or you're moving from like the equator to the North Pole, or if you're moving forward whatnot. Sometimes you might be going through some like electromagnetic waves where gravity might change, or sometimes like you might carry a lot of weight on you, and in those situations you might think, oh, I don't weigh that much. In those cases you need to have a factor of safety higher than 3. So why I'm saying that is, how much, okay, my logic is, how much additional weight does a human carry? Average weight a human carries in a day. So basically, based on that's not something I was looking for, but then I could use. So top says you should carry 15% of the body weight, right? Okay, so the recommended body weight that a human should carry is 15% of their body weight. So our factor of safety should incorporate that into our calculations. Also, the payload is based on the average body mass of humans in different continents, right? Different continents, we need to simply have a using the principles of standard deviation deduce that of so I'm gonna get back to this in a 1 second before I explain to you what this is. So this is based on the average weight, right? So if you look at the standard distribution curve, I'm gonna close this, I'm gonna close this, I'm gonna get back to it wherever I can't. I don't think we use that one. We use this one and I don't need it anymore. Refer to it, whatever. Deviation. Okay. Think normal, let's say I used the wrong word. So the thing about it is, if you have a weight higher than that, a weight of a human might fluctuate. You might lend your friend who might be like twice the size as you. So if you buy thing or you know, if you buy a hover vehicle, if you get a hover vehicle that's rated for your size or your range, that means you're also doing a disservice to your friend. Your friend might be dangerous if they're borrowing your hover vehicle. So you need to have a factor of safety 3. You don't know if the same user is going to use it the whole time, so you need to have that. Let's say if somebody, our maximum is 80, right? So 80.7 times 3 is what? 242 kgs. Somebody who is like 240 kgs, if they decided to use that, you know, you could use that, you know. So using the principles of normal deviation, we could use the factor of safety. So I'm going to explain to you what normal distribution is, right? This is your mean right here, and if you look at it, the mean, if you go from the third standard deviation to the mean of the data, it covers about, if you divide 68.3 by 2, that's 34.15, and plus this data. So you are looking at, if you go at the mean of the normal distribution, if I really look at it, right? So if I'm at the mean of the normal distribution, this half of the mean is 60 or almost 70% of the data. So like if you have 70%, that means you want to have that 75 percentile, you know, like you want to have the 70% of your day. I don't think I'm explaining it the best way possible. Just understand this. So you're at the mean, you divide this by 2, what you get is you're gonna get a half of the data, and then what you're gonna do is you're gonna do multiply that by 3, and then you're gonna reach this other maximum, and then if you divide that by 130, you're gonna reach this other one. Get it? So you're gonna get up to 99.7% of the data. That's how I basically think. Okay, I might be going totally wrong and I might have understood it totally wrong, but then if you're at the mean of it all, you're at like 34.1%. That's basically 34%. And if you wanted to reach to like 99, what you do is you say 33 times 3 is what, 99%. So yeah, you can't go 100%. That's the idea I'm using. So you understand that factor of safety at the mean is 33% of the total data spectrum, right? To reach up to 99% of the data spectrum, you use a factor of safety of 3. I know there's a principle to do this. I can't think at it at the top of my head. Why do we use design logic behind using factor of safety? Yeah, this should help us. So they use this, but I'm going. So if you really look at it, yeah, so see, there's a lot of other stuff going on, but basic thing that I'm gonna use right now. So yeah, you have to do all of this. This I hate, failure mode and effects analysis. I hated this a lot. I had to do a lot of other BS. And I did that, and I'm not gonna bore you with a lot of other stuff, but yeah, I hated that. So yeah, I think they're using normal distribution for this. So my reasoning is, okay, so you have your, like, this is basically how I'm designing it, and if there's a reason, guy, just tell me why. So you are at 33% of the data, factor of 3. I think I'm just butchering it at this point, but then factor of safety. No. What was it? Normal distribution. So I'm gonna do is put this here, and my work is done for that part. So you see the logic behind it. I know it's shady logic, but I'm using that number off the top of my head. But this is what I've done like most of the time, and I think it's a good enough design reasoning to do that. For like, if you go into actual manufacturing, like the other side. So you have guidelines for those, right? For each sector, you follow those. It's very easy. For me, there's no guideline for a hover vehicle, right? I have to come up with it on my own, and then it's just the starting design phase. So I'm gonna go with the least reliability. See, reliability, I hate it so much. You have to do so much probability in that. I hate doing probability. And my probability teacher was like such a, like, I didn't even understand the whole course. Like, it was about ships and using, it was based on much more electrical and less on the design portion. And they used to do like all electricals only, and I was like, what? Like, I didn't even like see the need to do like probabilities for the electrical part. I don't know. So yeah, so you have a factor of safety of 3, and if you're using this book, yeah, you need to build these pyramids. Bullshit, I can't use this. Logic behind formula for factor of safety. I guess we're caving into Google, okay? I should have just used Wikipedia and then cited the source. Yeah, we're gonna quote this. Don't tell me I did so. You wanna see some magic right here? Boom. So yeah, you're using that, and I'm going to use this formula right here. Failure load, design load. That's it. Failure load over design load. Right? So minimum weight threshold. So for that, so minimum weight threshold for that would be, so your design load is at what, 57.7 kg multiplied by 3 is equal to 57.7 divided by 3, 173.1 1 kg. That's your minimum threshold equal to maximum weight threshold equal to, we're at 80.7 kg multiplied by 3 is equal to 80, 242.1. I remember that. kg. So you have that, right? So you have your weight threshold and minimum weight threshold. Let's bold that. So you have that. It's very easy. It's very understandable. Since you have that, you can move on into, I think we quoted this, we quoted that, we quoted that, we quoted that, we quoted that. So we're good for now. Now let's move into how do we power the vehicle. So what were the questions? What is the minimum maximum payload? We've answered this. Let's for now, at least for now, that's done for now. Okay. How do we power the vehicle, right? Let me just explain this. To be honest, I'm gonna insert a break. I don't think I need that. I'm gonna post it on blog anyways, guys. So how do we power the vehicle? That's the question, right? For this, okay. Remember this? Remember this? Okay. This is a good point to start off because they're trying to do something that's really close to what I'm trying to design, right? So based on this, they have a useful load. I've come up with this. I've not come up with this other part. This part, I've come up with this, right? This is a good starting point for me. Okay, for me, it's all about the payload. My primary design constraint is payload. These are my primary design constraint. Design specification based on that, but then my primary design constraint is payload for me at the current moment because that's the first thing I approach. My mind goes, okay, I want to carry this much load. That's it. Now I need to decrease the cost based on that. That's the whole process. So let's explain that. The primary design constraint is the payload. I don't really care right now if it travels like what for 7 seconds, 8 seconds. That's all like out of the blue because I'm trying to make it so that people can use it on a day-to-day basis. We're gonna explain that in the other sections, like what are the use cases. So for part 2, we're gonna describe on the use cases, right? So for part 1, we're only doing this. For part 2, we're gonna do the use cases, and I'm just gonna explain that. For right now, the primary design constraint is the use cases. The use cases, time, and mileage will all be based around the payload. The primary concern is that the vehicle is able to carry the payload as demanded by the designer. So how I'm thinking is, so you have this device right here or a vehicle right here. You don't want that vehicle to go like 1,000 miles. It only carries like 1 kilogram. Okay, so I'm gonna explain to you in terms of a product that's already out there. Okay, just to explain my logic, how I'm going with this. You know what a drone is, right? For prime air, no relation, no nothing, right? They do this. They made this vehicle, but then they only do this for the packages, right? They have a certain limit of packages, like a weight that they can carry. For me, that's the main problem. if I make a device that's only going to deliver 1 kg, it's not going to be a vehicle. It's just going to be a drone for delivering packages. I'm not trying to do that. What I'm trying to do is, my thing is, I don't want it to go for 300 hours if it can't carry a human. I want it to carry a human. That's the first primary concern. So the use case of time and model will be all based around that. So we're gonna explain that based on this. The power needed to be. I don't think I'm gonna dive into. Let's just change it a little bit. Let's not make it a question, okay? Just thought about it. I don't think we're gonna do a lot on the design specification. As much as I'm thinking about it right now, these are only 3 of my concerns, like the primary. These are the primary concerns of design. Yeah. To be honest, I don't care. Must the payload. So you understand the logic I'm following, or if you don't, okay. I could reach out to these folks over here, these nice folks, but then it would leave out the idea that I'm not. Oh yeah, I'm not trying to get into patterns and everything. So my logic, how I'm envisioning is how to calculate the power delivered to a drone. You use technologies. I'm not trying to do. They've gone into energy use and life cycle greenhouse gas emissions of drones for commercial power. They've gone crazy here, people. What I'm trying to look at right now. Okay, one more thing. If you're doing research, you need to use multiple resources, okay? And So UAV thrust to weight ratio. Okay, that's what I was looking for. So what is thrust? It's the amount of the damage ratio of yeah, we need to quit that. We need to figure out the thrust to weight ratio for our vehicle, right? So since we already have the minimum and maximum weight required to so you already have a since we already have the maximum minimum, right? Oh yeah, let me explain to you this little bit. So you have 57.7 kg, right? And you have the normal distribution curve. And I just remember this off the top of my head. So you have that normal distribution. So you have your normal distribution right here. So you have 57.7 kgs right here. If you do that by 1/3, right? 19 but if you multiply it by that by 3, one go there. So you are going to carry 19.3 kgs right over here. But if it exceeded and the mean average kg, so what I'm trying to explain here is I'm such a bad explainer, but anyways, so your average body mass is this, right? But then your largest body mass for Asia would be 173 kgs. So if you had to sell this in Asia, you'd have to sell at 173.1 kgs, right? Correct? So Northern America is the same thing. If you decide to go the other route of minimum factor safety, it'd be good. So why I'm doing the minimum weight threshold and the other why we're doing that is because we need to figure out thrust to weight ratio. I think it's all coming on along together now, much more easier. I don't think we need to do cost today. Do we need to? I don't think so. Yeah, let's not do cost today. We'll do that some other day. Use cases, cost, time. Yeah, let's go back to the matter at hand. Okay, thrust to weight ratio. So this is what we're gonna use. So we're gonna calculate the thrust to weight ratio of I think this is for the Asia and this is for I don't know. It's gonna make sense as I go along. So one other thing. I don't need to explain this to anyone. Maximum mass equals, I'm gonna use 9.81. Think they use this. I don't know. Yup, they used one, right? I'm gonna use one. I'm gonna cite one. Maximum weight is maximum mass times absolute due to gravity. Saying they're using 9.8065 665 80665. I remember it off the meter per second. Two 42. 2,374. I'm just gonna copy this, and this is going to be that. And this is going to be that 2,375. Which is almost 2,375 Newton. Similarly, minimum weight. Since I explained to you what how I did that, I'm not gonna do the whole calculation again, and I'm going to do this 57.7 times 3 times that. I'm just gonna do that, which is this, which is also this just increases our 1,700 Newton. So here's the thing. If you want it to be suspended in the air, thrust to weight ratio for hovering. According to the manufacturers and similar standard, the thrust to weight ratio for drones at half throttle, which is just throttling the motor at half throttle, should be at 2:1 ratio, which means So therefore we can now calculate the thrust required to develop our vehicle. So we can do that now, right? Thrust required equals to omnimotor calculator. Since we're using the electrical motor, this might be useful, but omnimotor. And I will also write, but there is a concern that this design is based on electrical motors in drones. It might need some changes if we use alternative power sources such as steam, because in design you never know what might go wrong. So I'm just thrust required at 2:1 ratio is thrust to weight ratio multiplied by payload. So maximum thrust is 2375 by 2, 4750 Newton for Newton at a given second, I think. Minimum thrust is Newton. I'm just gonna explain this. 2 multiplied by payload. Okay, makes sense. We have the two parameters. Remember that. So we can use this to so we're gonna change so we can use this to do something else in the next video. We're going to do the use case, cost, time, design, specification, and mileage based on that. But use cases. So for this use cases, we're going to choose for now is electrical. But I think if you use steam, it's better. But then I'm going electrical because it's very easy. And that's the one that you're trying to use. So yeah, we're gonna design a hover vehicle based on electrical motors, but then I might go for steam too. Okay, I might go for steam. I might not use motors to do all of that either. Let's do this. Oh yeah, your payload weight is something different, okay? Do I need to question that? Okay. Oh. Payload weight does not include the weight of the vehicle, and it does not include the weight of the power source. Just includes the weight. So for us, the payload is just that. For all intents and purposes, for all intents and purposes for our design, the total weight will be the weight required to. I might be just misunderstanding what the payload is. For our the weight required to move the vehicle, which will be calculated once we determine the power source and the design specification of the vehicle. So what I'm basically saying is right now we just need to figure out how much it needs to carry. I think at this time it will still carry the whole vehicle because we're still using the 3 times, because you're not gonna have do that, and then you're gonna have to multiply this by 2 if you need like 2 people riding on it. There's a lot of other questions out there still, you know. This is just the first phase of the thing. None. Let me just remove that. So yeah, this is it for today. If you want to see more, just go click on the other one. If I have uploaded it, there'll be a part 2 and it'll just seem much more easier to understand it. But yeah, this is it for now. We'll meet again. Okay, thank you. Bye bye.